Okay, today I've divided the lecture up into two different sections because they're really two different topics. So I divided it up so you could watch one or the other and it'd be easy to find without having to fast forward through them. So notice that this is 14A, class 14A. The next video is class 14B. So it's kind of just two things. So make sure after you watch this one to go and look for the other one. Now this one will be relatively quick to get through. So let's go ahead and kind of get started on this. So this is about programming DFAs. And so far, what we've had is this concept of regular languages. And by definition, a regular language is one for which there exists a DFA. So if you have a DFA that exists that defines a language, you know that's a regular language. Conversely, if I have a regular language, I know that I could make a DFA for it. And we've learned that that's possible because if I have a regular expression, I can make that into an NFA. I can then make that NFA into a DFA. So no matter if I have a regular expression, an NFA, or DFA, those are all regular languages. So we can make a DFA for any of them. And we know kind of an algorithmic process to convert regular expressions to NFAs, NFAs to DFAs, and then we could even minimize that DFA to make the smallest machine possible. And then we could write a program that actually simulates that or actually embodies that DFA. So that means that all of those define the family of regular languages. So any regular language we can have a DFA for, and then therefore we're going to look at how to program a DFA. Now, DFA programming is useful in a lot of different things. So for example, you have some pattern and you want to know, does this belong to this language or not? And that can be useful for a lot of different things, from writing a compiler to say, is this a variable name? Does it fit the rules for a variable name or does it not? Does this fit the structure that we're expecting for some value to be in this configuration file or not? And so there are a lot of cases where we have some pattern of characters and we need to either categorize that as which type of thing is this? Is this a hex constant? Is it a numeric constant? Is it a floating point constant? Which one of them is it? And so we need some way to categorize those kind of patterns of symbols. And it could also be patterns of symbols like for other purposes as well, not necessarily just something out of a file, but something where you input some pattern and the machine responds to it in some way. So since any regular language can be represented with a DFA, and we can make that from any of them, then we're going to look at how do we program that DFA. So if you have a regular expression and you want to say, hey, does this pattern of characters match this regular expression? Notice there's a really easy path to get there. You'd say take this regular expression, use the algorithmic way to create an NFA from that, take that NFA, use the algorithmic method to make a DFA from that, and then write the code that embodies that DFA, and then you can feed any string into that DFA, and it will very efficiently say, yes, this matches this pattern, or no, it does not match this pattern. And notice the cool thing about DFAs is that they are super efficient because they just process the characters one at a time, and when you get to the end of the string, they report yes or no. So it's very efficient. The processing is very efficient. You never have to backtrack. You're never making some guess. You're not looking ahead and looking backward, and you're really just processing one character at a time. So the complexity of it is very kind of low. It's very high on the efficiency scale because it's order n. You just run through all n characters of the string, and by the time you hit the last character, you instantly know, yes, it's in that language, or no, it's not. So how are we going to program that? Well, it's simple. We're going to simulate the operation of the DFA. All right, so for example, here's a DFA, and this one is just, the alphabet is just A's and B's. But to simulate that, we're going to, just like we would looking at it, we're going to say, okay, it starts in state Q0. And if I'm in Q0 and I get a B, I loop back and I stay in Q0. If I'm in Q0 and I get an A, I go to Q1. And so notice that what we're going to do is just use a variable to keep track of what state we're in. And that, since it can only ever be in one state at a time, you can store that in a simple scalar variable like an integer. And in our case, you could say, like, for example, if we were in C, we could say int state equals 0, semicolon. Or if we're in Python, we can say state equals 0, and that's the state we're in. And then what we're going to do is we're going to just process things one character at a time. Say if I'm in state 0 and I get a B, keep the state as 0. If I'm in state 0 and I get an A, go to state 1. And notice we're going to have kind of a if statement for every one of the states, or could be a switch case. But we're going to have a block of code for each case, for each state, and we're going to have a if statement or a select for each one of the characters in that state. So if I'm in 0 and I get a B, stay in 0. If I'm in 0 and I get an A, go to 1. So we just need to write the code to process one character at a time. So the way we're going to do that, I'm going to show you 3 different methods here that are somewhat related, but we're going to start off with method 1. And what it does is it requires the transition function to be embodied in the code as, first, a loop that goes through every character of the string linearly. We're just going to buzz through it one character at a time. And then within that loop, every state is going to have a code body that could be implemented with an if, else, or a switch case for every state. And then for each of those, we're going to have a sub kind of either switch case or if, else, construct that then switches based on the characters of the alphabet. So method 1 is really easy to implement. Yeah, really in any programming language, even low-level languages like assembly or machine code, you could implement these in. But there is a more data-driven approach, which we're going to look at when we get to method 2. But let's look at method 1. Let's look at some code for what we're talking about. Now, I know this is kind of small because I wanted it all to fit on the screen at one time so you could see it. But looking at the way this code is set up, you'll notice that what we have is this. I created this. This is in Python, but it's really easy to convert this to any other language as long as that language has some sort of loop and some sort of decision statements, and even things like assembly language and machine code. You could do comparisons. As long as you can do comparisons and branch to other places, you could write this code really easily. So this is embodying this DFA that we looked at earlier. So let's look at how this works. So the first thing we do is we're passing in the input string, and notice there's our state variable being set to 0 at the start before we actually process the string. So we start at state 0. Notice that's shown in our diagram over here with the start state as 0. And then what we do is we go through every character in the input string. And in Python, we just do that by saying for ch. And since input string is a sequence, for ch, that's for character in this string. And now we say if the state is 0, and then inside of that, we say if the character is A, then the state goes to 1. So notice we're just modifying the state variable based on what input we received on this character. And then we're saying else if character equal B, then state equals 0. Now state was already 0, so in some way we could have just put pass there, but to make it clear that what's going on, we just put state equals 0 there anyway. And then we have this else that basically returns false. In other words, if we encounter a string that's not in our alphabet, the DFA should immediately report failure. That does not match this language. It could never match because it had a character that was unexpected that showed up. So notice this else where we're returning false there. So in other words, if I get an A, I go to 1. If I get a B, I stay in 0. If I get something else, anything else can't be in this language because it's a character that's not in our alphabet, immediately return false. And then we do that same kind of thing for every state. So if state is 1, so here's state 1 over here. And let me turn off the picture of me so you can see the entirety of that thing. All right, so notice that state 1 on an A, we stay in 1. On a B, we go to 2. And I need to fix this down here because this is on an A goes to 1 here. Quick in my code. All right, so let me fix, let me go back and fix that. This needs to be if we get a B, our state remains 2. Okay, so notice that this code directly models what's going on in this. If state is 1, and we get an A, we stay in 1. If state is 1 and we get a B, we go to 2. And then in state 2, if state is 2 and we get an A, we go back to 1. If state is 2 and we get a B, we stay in 2. Now, after we're done processing all those strings, we have one last thing to do. We have to say if the state is 2, because that's our final state, then we return true. Otherwise, we return false. And notice I didn't use an else there because return will immediately exit as soon as we hit that, so there's no need for that. So this is kind of the else by default. So if we had more than one final state, we could say if state equal to, or state equal whatever the other state is, or you could actually list as many, or in Python you could say if state in, and then make a sequence of all of the ones that are final states there. And if it's one of those final states, we return true. If it was a non-final state, we return false. Now, one thing that I did leave out here is sometimes when you code these, it could be useful to have an else return false, meaning if it got into a state that was not one of these states that was defined, then we immediately return false. Also note that you could have trap states modeled as, excuse me, you could have trap states modeled as any state where it enters that and will never return true from there. You could have it immediately return false at that point or consume the rest of the characters and return false. But having it exactly model that. So notice to change the DFA, what DFA this models, we just change how many if state equal things are to match the number of states. And then we change the if statements inside of here to say, on what symbols of the alphabet, what state do we go to. So the transition function is actually embodied by this if statement that's inside of each of these state variables. So that's the state symbol pair transitioning to this other location. So in order to change the DFA in this case, we need to change the code. All right, so let's move on here. Let me turn that back on. Okay, now the method 2 is going to be a little more data-driven, meaning that rather than having to change the code, we're just going to change some data. In method 2, rather than storing the transition function as those kind of select case or if, else if thing, we're going to actually store it in a dictionary or an associative array, if you're used to C++, a map. So anything where you can associate some data item with some other data item. In some languages, that's called a hash. Associative array, if you're used to Python, I think most people never had exposure to Python, so that's a dictionary. So in other words, you look up some key that's associated with some value. Now notice the way that this DFA simulation works, the way we're going to store that is this is exactly like the 5 parts of the formal definition of a DFA. So we have our alphabet, which was sigma. I can't really type sigma as in programming, so I wrote it out. And then we have our state set, which in our case, and actually this one does not match that. Yeah, I'm going to pause this real quick and I'm going to make those two things match. Hold on one second. Okay, so we are back. And let me, now this matches that. Apparently when I cut and pasted it, I cut the wrong example in here, or pasted the wrong example in here. All right, but so sigma is A and B. Our state set is 0, 1, and 2. So 0, 1, and 2. And then this delta is our transition function. So our transition function is going to map state symbol pairs to resulting states. So this is our, actually looks just like all the elements of our transition function. So notice 0 on an A goes to 1. Notice 0 on a B stays in 0. 1 on an A, or the pair 1 and A go to 1. 1 and B go to 2. 2 and A go to back to 1. 2 and B stay in 2. Our start state is Q0, and our final state set, in this case, only has 1. That should be Q2. Let me fix that. Q2. Again, left over from our cut and paste error. All right, so moving on now to the next thing is now what we're going to do is we're going to make a function that uses this data to simulate the DFA. In other words, it's going to start in whatever the defined start state is. It's then going to go through the string 1 character at a time, just like we did before. But each time what it's going to do, it's going to take the state we're in and the symbol that we have, make a pair out of those, look them up in the dictionary, and then that becomes our new state. All right, so let's look at how the code for that works. Let me fix this too. Okay, so notice that for this, here's all the data at the top. Here's my function, state equals start state, using the data entirely. And now for character in our string that we passed in. And then we're going to say if the character is not in sigma, so in other words, if it's not in our alphabet, then we immediately return false. That's kind of like the else on each of those if-else's we had earlier. We're saying, hey, if the character that we're on is not part of my alphabet, immediately return false. It cannot be in the language because it had an unknown character. Then the next thing I do is I say state equal, look up in delta, the pair of the state we're in and the character we're on, and then that is going to look up what's on the value side of that key value pair. So this is the key. And the value is the resulting state, which now changes our state that we had set up here. The state variable now has been updated. And then I added this little bit of code to say if the state is not in our state set, we return false. So that would allow me to make a trap type state that immediately returns if we wound up with something that was not in our state set. You don't really need this if statement here. If you write out a full DFA as a total function and have a trap state that just eats up all the characters, you could do that. But this could be used to short circuit that. And then after this for loop, I basically say if the state that I was left in when the thing ended was in our state set final, was one of the final states, then I return true, otherwise I return false. Now notice, this is similar to what we did before, but we've done away with all that if, else if stuff, or the switch case that had to deal with all the states, and we did away with the thing. It's all of the functionality is kind of encoded in this one line here, really, where we're looking up in the dictionary this pair of the state we're in and the character we're on, and that results in the new resulting state. And notice that what's cool about this is to change the DFA, I don't have to change any of this code. This code is very generic. All I need to do is change this data that's up here. What does my alphabet look like? What does my state set look like? What's the transition function look like? What is the start state? So this looks exactly like a formal definition for a DFA. We can give this a formal definition, and this will run through the code and process it and give me a yes or no answer without ever having to edit this code, only the data. Now that brings us to method 3, and method 3 is kind of a little bit more of an object-oriented approach to this. And with method 3, what we're going to do is we're going to encapsulate all of that within an object that holds the data and the code together. So in other words, we're going to have some methods that actually do that, and that way we're going to be able to create an instance object of one of these DFA simulators, give it the data when we create it, all of the parts of the DFA like this when we create it, and then it's going to now have this machine that we can feed strings into, and it will return yes or no. So let's look at an example of that one. All right, so in this case, and let me pause for 1 second because this has the same cut and paste error since I... Okay, so looking at this code, I went ahead and fixed the only part I had to change was this stuff down here. But notice that here's my object. I make a class for that DFA. And what I do is in the constructor, I pass in the start or the state set, the sigma, meaning the alphabet, the transition function, dictionary, the start state, and the final state. So this is the same stuff we had in the one previously, but now we're putting those inside of the object itself rather than having them be these kind of global variables that get accessed. And then inside of there, we have this process string function, which now has the code that we had before that goes through every character one at a time. I also have this reset that allows me to reset the state back to the beginning if I want to reuse this machine. So I use it once, I get to the end. You could also build this self.state equals start state into the process string function. But by having the reset and the process string be separate, that would let you process little bits at a time and then see if it was in a state. But then down here, this state accepting, that tells us whether we're in a final state or not in a final state when the thing is done. So what we can do is we can call process string. It'll return yes, you're in a final state when you ran out of characters, and you're not. You could feed it more characters if you wanted to, or you could reset it and start the whole thing back over again. But notice that here is when we create this instance of this class, we pass in all of the data it needs, all of the parts of the quintuple of the formal definition of the DFA, and now we have this DFA machine. Now to use it, notice I did a reset. We didn't really have to do that because it was already in that the first time, but then we pass it a string, and it will return either true or false. to return yes, that was in the language, or no, it wasn't. And then we could reset it and feed it another string and try again. Now, if you wanted to get rid of the reset and make it so it just always reset, you could just put self.state equals self.startState up here before this for loop and get rid of that method. But there are cases where it's useful to reset it and feed a little bit, see if you're accepting, feed it more, see if you're accepting. So this is a little more flexible in how this is set up. But notice that this is a really cool way of doing this, because the only thing we have to change is the data that make up the DFA. We just pass those in. And we have this instance that now embodies that machine. So no editing of code, only data. And that DFA that we feed this could come from a lot of different places. For example, we could have it where we have a regular expression. The regular expression gets algorithmically turned into an NFA. The NFA gets algorithmically turned into a DFA. We minimize that DFA to make the smallest machine possible from it. And then we pass that to this class to now have a machine that will accept strings from whatever language the regular expression started with. And regular expression matching, notice that this is super efficient, because notice that how simple the code is. We're just running through every character in the string and updating the state. And when we get to the end of that, we say if we are in a final state, we return true. Otherwise, we return false. All right, so that was method 3. Now, before I go on any further, I want to announce the midterm. The midterm is going to be held in person in ATC, the Advanced Technology Center, room 326. And that will be 1 week from today at the normal class time. So 2 o'clock to 4:15. It'll be a paper exam, so come prepared with a pencil or a pen, and you'll write on the test itself. If you want some scrap paper, you're certainly welcome to bring that. The class itself, or the exam itself, is also open book, open notes, but you cannot use electronics or the internet. So if you have notes from the class that you've taken, you might want to print those out if they're in electronic format. Otherwise, bring your notebook. So you're more than welcome to use that stuff. I will be posting a study guide today as well. Look for that. And there are actually 2 versions of the study guide I'm going to post. There's one that has the answers and one that does not. So what I would suggest you do is you go through the one without the answers, try to solve all of those, and then look at the answer guide for that to see if you got the right thing. If you didn't get the right answers for those, then make sure to ask questions. The other part of this announcement is I'm going to be available on Wednesday, meaning in 2 days. And I will be in ATC 326 during the normal class period, 2 o'clock to 4:15, to help answer questions, go over assignments and homework, anything you've had trouble with. I will be in class from that normal time, and it will just be a study period for preparing for the midterm. So I would suggest, if you need help or you have questions, show up to that period, and I'll be around to help you that whole time. Also, keep in mind that if you're stuck on something, send me an email or a text message, and I can certainly come in and sit down with you and explain stuff if necessary. And I know some of you have already taken advantage of that, but make sure to message me if you need help. But I will be in class on Wednesday, 2 to 4:15. Okay, so that's all for part A. Continue on for part B. Everybody stay safe, and we'll pick up the lecture in part B momentarily. Make sure you watch both of those and make sure you're ready for that midterm. That's it for part A. See you soon in part B.